Okay, surface integrals. So what we want to do, okay, one application that we want to understand in multivariable calculus is the concept of flux. Okay, how many have heard of flux in other classes? Flux rates? And maybe not everybody's heard of it. Okay, Juliana's heard of that in physics. Okay, absolutely, absolutely. So if you have a surface and you have fluid flowing through the surface, you want to be able to determine the rate of flow, okay, the rate of flow of the fluid through the surface. And that's how eventually surface integrals are going to help. But first, we have to mention that the relationship between surface integrals and surface area is much the same as the relationship between line integrals and arc length. Now, let me just go back here for a moment. Give me just one moment, because we're going to need to refer to something here. Hold on. I have to go into the ebook fresh. Okay, I want to show you something we'll be referring to here. Okay, hold on here. Okay, so recall back in section 12.6 when you learned about surface area. We studied surface area by taking we treated the surface, whether it's a cone, a paraboloid, or a cylinder, we treated the surface as a parametric surface that could be traced out by a vector function of two parameters, u and v. Now, sometimes instead of u and v, you might have x and y, you might have r and theta, it'll vary, okay? But the point is that this vector function of two parameters, as u and v vary in the UV plane, you can trace out a surface. This is really just a refresher of section 12.6. As u and v vary in the UV plane, you trace out a surface. And for any point on that surface, you can create two tangent vectors, r sub u, and r sub v, that are tangent to two space curves on the surface. Each space curve is generated by taking your vector function of two variables and holding either u constant or v constant. And if you hold, for instance, the u constant, you'll get the space curve C1, and then the r sub v is the tangent vector to that space curve at the point P sub 0. If you were to hold the v constant, you would get space curve C2, and the vector r sub u would be the derivative vector of that vector, and you know, it'd be a tangent vector. And so we use this idea because we needed, like as they show here in figure 2, and this is back in section 12.6, we had a surface. One moment. Okay, we had a surface here in figure 2 on the right, and we wanted to, in order to find the surface area, we needed to find the surface of the ijth patch on the surface. And so what was done is well, if you want to find the area of the whole surface, you break the surface up into patches and find the area of each patch. And of course, a patch is not, I mean, you could think of a patch like here you see in this picture, and you can approximate the area of that patch with a parallelogram. But as you see in this figure 3 from section 12 points, section 12.6, the hold on, let me just make sure, I believe I do have that section right. Yeah, surface area. Yeah, so the parallelogram approximate, like the patch, right? The patch is not a perfect parallelogram. Okay, and there's like the patch has a hump on it, perhaps. But if you were to look at the bottom corner of the patch, and you could draw vectors, like in figure 3A there, that go along the side of the patch. Now, if you were to take those vectors and scale them by delta U and delta V, as they do in figure 3B, the area of the patch starts getting well approximated by the area of the parallelogram. Essentially, that parallelogram in figure 3B approximates the corner of the patch very well. So ideally, if you take smaller and smaller patches, you can approximate them, therefore, with these the area of the parallelogram with formed by vectors delta U times derivative vector R sub U and delta V times derivative vector R sub V. Now, how do we find that the area of that little green parallelogram? Well, remember that back when you learned about finding the area of a parallelogram, you learned remember that the absolute value of the cross product of the two vectors that form the parallelogram, that would equal the area of the parallelogram. How many of you recall that back from section 9.4 when you learned about the cross product? How many recall that? This idea that okay, good. Juliana recalls it, and but instead of our vectors A and B, we have those vectors delta U times R sub U, delta V times R sub V. Well, if you take the absolute value of the cross product, you can factor out the delta U and the delta V. And so that's going to equal the absolute value of the cross product times delta U times delta V. And this is going to be useful when we talk about these surface integrals in section 13.6. So let me go ahead here and now go back in fresh to 13.6. I just wanted to refresh your mind a little bit here. 13.6. One moment here. Okay, so all right, they make a comment here that they're going to define the surface integral, okay, of a function f over some surface S, such that in the case where the function were equal to 1, the value of the surface integral is equal to the surface area of S, and that's fine. That's fine. So let's proceed here. So again, there is the vector function of two parameters that traces out the surface. And what we're going to do now is we're going to take the, like there's a function, okay? There's a function, okay, a function of x, y, and z. And for every point on the surface, we're going to evaluate the function and multiply it by the area of the ijth patch at that point. So every point on the surface is, there's a patch basically that it includes, and we're going to multiply that area of that patch times the value of the function at the point at that patch. So it's much like a line integral, only with the line integral, the way yeah, and then we're going to add up all those values. So like pictorially, this is what you're doing here, okay? In figure 1, there's if I go down a little bit, there's the surface, okay? There's the ijth patch, there's a point on the ijth patch. Take the area of the ijth patch and multiply it by the value of the function at that point, p sub ij. So it's analogous to the line integral, except with the line integral, what you did was you took the value of a function at a point along a space curve and multiplied the value of that function by a piece of arc, by a delta s arc length. Okay, it was a piece of arc length. Here you're taking the function and you're multiplying it by a piece of area. That's what a surface integral is. Okay, and what we want to do is we want to add up all those values, the values of the function at each point multiplied by the area of the patch at those points. And if you take the limit, if you sample more and more points, you'll have smaller and smaller patches. And if you take the limit, you get a double integral. You get a double integral with respect to ds, capital S. Okay, and that's called a surface integral. Okay, that's called a surface integral of the function over the surface S. Okay, are there any questions so far? And this is analogous to how we developed to the line integral concept. Now, what we want to do is we want to evaluate this surface integral. Well, of course, the parameterization, I mean, the vector function of the two parameters that traces out the surface is a function of parameters u and v. So we would like to get this double integral in terms of the parameters u and v. Well, let's keep in mind how we got to that Riemann sum, that double integral. It's based off of that. It's based off of that double Riemann sum, right? Based off of the double Riemann sum. So let's substitute in for delta S sub ij the expression for finding the area or approximating the area of the ijth patch. Well, that would be equal to the cross product of the derivative vectors r sub u and r sub v times delta u times delta v. Okay? And so all we're going to do is we're going to substitute in that expression for the area of the ijth patch into this double Riemann sum on the right. Okay? And when you do that, the double integral on the left, okay, the double integral on the left will equal this double integral. So the function of x, y, and z, well, the points x, y, and z are those points are determined by your vector of functions u and v, because as r of u and v, as u and v vary, you're scratching out, the tip of that vector scratches out the surface. So the vector, the tip of that vector, which gives the points on the surface. And then the ds will become, I mean, I want to say this the right way, the because delta S is equal to the cross product of R sub U and R sub V, delta U delta V, then the ds would just be then the cross product dA, where dA is, hold on here, dA is equal to delta U delta V. Let me just see here. I have it. One moment. Let me just write this right. Let me just see if I need to write anything down here. Okay, maybe I can write this down in the whiteboard. Hold on. So, okay, so here, I equals 1 to m, j equals 1 to n of f times p, f of pij times delta s sub ij. But delta s sub ij is equal to the cross product, hold on here, the absolute value of the cross product of RU with RV times delta U delta V. And the function evaluated at point P, that point P sub ij, is the same as the function of R evaluated at some parameter values U and V. So in terms of then when you take the limit, okay, as m and n both go to infinity, this here will approach a double integral over some region S where your function of U and V is here. Okay. And then you have the cross product of RU with RV. And then du dv, which they call dA. Okay, does that make sense? This is what they have on formula 2. Okay. And they assume the surface is covered only once as U and V vary. This is going to be, this is how we compute a surface integral. This here is your surface integral. So when you see the big D, capital S, that stands for a surface integral. Okay, so this, I'm just trying to make a few connections here. Are there any questions on that? Maybe give me a thumbs up if you're okay. Okay. Good, good. All right, well, let's go back to the book here. Very good. This is all in the recording. So they comment here. Let me just hold on here. Let me just remove this. Try to highlight that. And I'll highlight this too. Good. So they comment here that this surface integral, absolutely beautiful, the surface integral should be compared, the formula for the surface integral, the top yellow box, should be compared with the formula for a line integral. And you see kind of a similar, the form of the integrals is basically similar. You see that? So there's kind of a nice connection there. Yeah, yeah. Thank you, Juliana. So they just want to kind of anything they can do to make it a little more comfortable for you. And also, they observe that if you wanted to find the actual surface area of your surface, all your function of x, y, and z would just set equal to 1. So it's like when you find the volume of a solid, what's the function equal to? You know, for like if you're using a triple integral to find a volume of a solid, what's your f, x, y, z equal to? You should know that, right? What's it equal to? What number? For a triple integral. What's your integrand equal to? 1. That's right, Ellie. Good, good. So, all right. Now, again, this result relies on if you're going to use this formula here from section 13.6, it relies on you finding the parameterization of your surface. Okay, and I always like to use this formula because it works all the time. It works all the time. Like if you were to have a cylinder, if you were to want to find a surface integral over a cylinder, a cylindrical surface, you would need to use this formula. Okay, but if your surface could be written as a graph, in other words, if z were a function of x and y, for instance, then you could adapt this formula to another formula. Okay. So if we go over here to where it says graphs, okay, let me see if I can I want to try to highlight that. Hold on. So any surface that can be written as an equation z equals a function of x and y can be regarded as a parametric surface with those parametric equations. Your parameters could be x and y, and then z is a function of x and y, right? So x and y are your parameters. So if you then do the derivative of r with respect to x and the derivative of the r vector with respect to y, that's going to equal what you see up there, what you see there. Okay, it will equal those vectors there. And if we go and take the cross product of those vectors, okay, you will get this vector here. you will get that vector. Negative partial. Remember, z is equal to, z is a function of x and y. That function is g. So the cross product of r sub x and r sub y would equal that vector. You could work it out and show it. And then this means then that the magnitude, the length of that cross product vector would just be equal to that quantity, the square root of that. And so formula two, which was the formula 2, which was this formula, can be replaced with this formula. Okay? So it's important to be aware of it because sometimes I'm sure like the help aids, the watch it videos mention this formula. Okay, but it only works if z is a function of x and y. Now it would work also if like x were a function of y and z. You can adapt the formula appropriately. Generally, what I like to do, again, my style, is to not worry about all these different formulas, but work with the formula, work with the main formula, formula 2, which will work all the time. Okay, it'll work all the time. Of course, you'll have access to these formulas on the final exam. So that being said, let's go ahead here and look at an example of a surface integral. Let me give you a moment to copy this example down, okay? Okay, so so they're saying this is a surface integral. Evaluate the surface integral. There shouldn't be a period here, right? Evaluate the surface integral. How do I know that this is a surface integral? What's telling me that this is a surface integral? Can somebody take the pen, I'll put it in blue, and highlight something there that's telling me that, hey, this is a surface integral. I mean, suppose Suppose they just said evaluate and they didn't put these words, the surface integral. Okay, suppose they didn't put those words. Why is this a surface integral? What's telling you that? Could somebody underline something in the double integral that's telling me that, telling us that? There you go. Good, good. Thank you, volunteer, who did that. Appreciate it. The D sub capital S. Now, D sub little s stands for arc length, right? The little s is arc length. That's a line integral with respect to arc length. This here is a surface integral. This is a surface integral that we are computing over a surface. Okay, so please recognize the difference. Now, what is our surface here? What is our surface? The surface we're being given is part of a cylinder between the planes z equals 0 and z equals 2, together with the top and bottom disks. So this surface here is actually a closed surface, right? It's a closed surface because we have the cylinder itself, and it includes the bottom and the top discs too. So the bottom disc and the top disc. Okay, so you have three surfaces here. So to get this entire surface integral over this entire, this entire surface S, how many surface integrals am I going to have to compute and add? So we could call this like S sub 1 here, the top disk, the cylinder part, okay, like the can part, the side of the can, the cylinder is S sub 2, and then the bottom disk is S sub 3. So how many surface integrals am I going to have to compute to find the surface integral? 3. That's right, Madeline. 3. Okay, that being said, what we're going to do is we're going to work in order here, okay? We're going to work in order. I'm going to first of all find the surface integral for this top disk here, this top disk that is at the height of z equals 2. So let's go to the next page. Okay, there's a picture of my surface. The surface S is the union of surfaces S1, S2, and S3. Okay, so my surface S1 is the top disk, and I drew a little picture there. Okay, let let you copy down up to this stage here, okay? And then we'll talk. Please let me know if you have any questions. Take very good notes. I'm putting in a lot of detail. The book doesn't show as much detail as I'm showing you. And this example here is an example. It's an additional example to the book examples you have so that you can get variety. Okay, so all right, take a moment to copy it down. Okay, so let's talk about this top disk here. So, of course, a disk here, a disk right here, this surface S1, it's a circle. So you know in the parameterization you're going to have a cosine and a sine involved, and it's going to be in the x and y components because it's a horizontal disk. Okay, now this disk is at a height of 2. Every point on this disk, inside the disk, has a z value of 2. So that's my z value. But in order to get the entire disk, the entire disk includes not just the perimeter of the disk, but what's inside too. So even though the cosine of u and the cosine of v, the cosine of u and sine of u, when u is between 0 and 2 pi, that'll get you a circle, but you have to change the radius of the circle. And that's where the v comes in. And notice the v goes from 0 to 3. That makes sense because the cylinder has radius 3, so the disk has to have radius 3. So essentially with this parameterization, what you're doing is, you see, you're creating a bunch of circles with different radii, a bunch of concentric circles with different radii based on what the value of v is. Okay, and your final, if I draw, like, I'll try to be, here we go, here's like the big outer. For this big outer, the perimeter, what's the value of v? What's the value of v? For the outermost, I'll draw it for the rim of the disk. What's the value of v equal to based on this parameterization of that disk? What's the value of v equal to? All right, hang on. Let me go to the whiteboard. Okay, hang on a minute. Okay, let me just write down this here. So my top disk, one moment. Okay, my top disk, I'm telling you that my parameterization is this. R of uv equals v times the cosine of u, v times the sine of u, that's the second component, and 2. And u goes from 0 to 2 pi, and v goes from 0 to 3. So let's go ahead here, and I'm going to put a point here. Okay, now we know the disk is at a height of 2. So let's focus on the x and y components, okay? The x and y components. So I'm going to draw here a circle. This circle has radius 3, okay? This circle has radius 3. So for this circle, for this outer circle, okay, I think we can probably, this outer circle is a space curve, right? It's a space curve, okay. Okay, do you see that that outer space curve would equal R of u and 3, which is 3 cosine u, hold on, 3 cosine u, 3 sine of u, and it has a height of 2, okay? But let's just focus, you know, like here's the, you know, there's the middle right there. Do you see that that space curve would have this parameterization? And of course, u is between 2 pi and 0. In other words, does this space curve make sense? Well, this space curve drew me a circle of radius 3. Does that make sense? Please give me a thumbs up if it makes sense. And it's at a height of 2. The circle's a height of 2 above the origin. Okay, Ellie, you're good with that. Ian, you're good. Okay. All right, good, good. Gordon, Charles, Juliana, excellent. Excellent, excellent. Now let me draw another curve here. Okay, so this had radius 3. So hold on a minute here. Okay, so this had radius 3. I'm going to draw another circle. Another circle. This circle has radius 2. So for this circle here, that's a space curve. R sub u of 2 would be then 2 times the cosine of u, 2 times the sine of u, and 2. And of course, u is between 0 and 2 pi. That would be the next space curve. For instance, that's another space curve. Two times the cosine of u. We kind of separate this a little bit. 2 times the cosine of u is the x component, 2 times the sine of u, and then the height is 2. Please give me a thumbs up if you're good with that. All right, good, good. Now, what we want, thank you everybody. Now, what do we want? We want the entire disk. To get the entire disk, let me just see here. Let me just do the center. Let me do one more here. Let me just do right here in the center. For the center here, that would be R of u comma what value? R of u comma 0. That's right, Juliana. Well, that's just going to get us 0, 0, and 2. Okay. And I mean, you know, sure, we can say let u vary between 0 and 2 pi. We can do that, but it doesn't really make much sense. But sure, not a problem. Try to separate this here. So give me a thumbs up if you're okay with that. If you're okay with that. So the middle point, the middle point right here. All right. Good, good. Now, what do we want here? What do we want? We want the entire disk. The entire disk. To get the entire disk, I have to take a bunch of space curves and put them all together to fill out the entire disk. Well, the space curves have different radii. The radii is determined by V. So that's why we have to let V be between 0 and 3. And of course, U is between 0 and 2 pi. And so the parameterization for this disk, for the top disk, then, is going to be R of UV equals the vector function, or the with parameters V cosine of U, V sine of U, and 2, where U is between 0 and 2 pi, allowed to range between 0 and 2 pi, and V is allowed to range between 0 and 3. Okay, does that help you see why that parameterization makes sense? Maybe give me a thumbs up if this was helpful for the top disk there. Okay, thank you, Ellie. Thank you, Juliana. Okay, thank you, Ian. Excellent, excellent. Thank you, Gordon. All right, so nothing strange here. You know what I mean? I mean, it might seem a little strange, but it doesn't have to be strange, right? If we just work with the fundamentals. So we can get a parameterization of a space curve, of a surface. Sure, sure. Okay, so my goal here is for students to be comfortable. I want students comfortable with this material. Okay. So let's go now back to the book, back to my example, back to the problem at hand. So again, now we are going to compute this surface integral by adding the sum of 3 surface integrals. And now we have a very good, hopefully comfortable feel for this parameterization. And notice what I do here. I know that ultimately I'm going to get a double integral, right, for to compute my surface integral. Well, I need limits on my parameters u and v. Well, u goes from 0 to 2 pi, and v goes from 0 to 3. So it's going to be a rectangle. That's my region D for my double integral. So now it's just easy. All I need to do is follow that formula 2 from section 13.6. I, will compute the cross product of those derivative vectors, r sub u and r sub v. The cross product will equal negative v times k. Notice, by the way, that vector, well, yes, that's fine. That's fine. So when you're ready now, we'll move to the next page and we'll go ahead. We have to find now the length of this cross product vector. All right, so when you're ready, we'll go to the next page, okay? All right, Charles is good, all right. Juliana, Gordon, and Ellie are good, all right. Okay. Just trying to be patient. Hyunu, how are you doing? You have it copied okay? Good. All right. Malik, how about you? Excellent. Okay, good, good. Okay, so let's find the length of this cross product vector. So the length, of course, well, remember what the cross product vector was. The cross product vector, RU cross RV, was equal to 0, the vector with components 0, 0, and negative v, which is just equal to negative v times the k vector. So the length of that vector is equal to v. Note that RV, our value of v, our parameter v, was between 0 and 3. So I don't need to worry about like having absolute value on this v here. So okay. Now we proceed forward here. So here's the surface integral across surface 1. And I'm using formula 2. So the function is x squared plus y squared plus z squared. Well, we know based on our parameterization of this top disk S1, x is v cosine u, y is v times the sine of u, and z is just 2. So okay, and then there is the absolute value of the cross product, or I'm sorry, the length of our cross product vector, RU, cross product of RU, R sub U, and R sub V. That's just equal to V. And notice I haven't talked about what dA is yet. I'm not going to decide what my, what am I going to integrate with respect to, well, I know it's U and V. But I don't want to bring that in yet. Okay, I don't want to bring that in yet. I'm not ready to bring that in yet. I want to do a little bit more here. So, okay, I'm going to simplify. The cosine squared plus sine squared equals, well, let me just point something out here. Hold on. So this is going to be v squared cosine squared u plus v squared sine squared u plus 4. Okay, that's going to equal v squared times cosine squared u plus sine squared u plus 4. But cosine squared u plus sine squared of u is equal to 1. And so that gets us a v squared plus 4. That's how I got that. V squared plus 4. It's a little bit like remember the movie Castaway with Tom Hanks. How many remember that movie, Castaway? That's how I think of these double integrals a little bit. All right, Hyunu remembers it. Has anybody else seen Castaway? I'm sure some of you must have seen that. Okay, Charles has seen it with the soccer ball, right? And remember, he's trying to get. Remember, he's trying to get off the island, right? And the tides. He has to get over the waves coming into the island. He has to get his raft over, and he has a sail, and he has to decide when to lift his sail up so he can like glide over the waves, right? And he says wait, and then he says wait, and then he says wait. Well, and then finally he picks the right moment, but he says wait, and that's kind of like what I'm doing here. I am going to wait to put in my limits until I'm ready. And now, now, hey, I'm at this stage here. Now I'm ready to put in my limits. Well, my region D, back on the previous page, my region D was a rectangular region, okay, with U limits from 0 to 2 pi and V limits from 0 to 3. So therefore, now I put the limits in. And what I did here is, I know you can compute a double integral. So the 3 dots mean left for you. I mean, in other words, you're capable of doing that, right? You're capable of doing that. That's left for you to do. So you get 153 pi over 2. That will be the final answer for the first surface integral. Okay, and are there any questions? Okay, give me a thumbs up if you're ready to move to the next page. We have to compute our second surface integral across the cylinder. Okay, good. How are we going to start, everybody? I want to compute my next surface integral across the cylinder. So what do I need to find first before anything regarding the cylinder? I need to find the cylinders. It begins with a P, kind of a long word. Well, not perimeter, Ellie, but right, the parameterization for the cylinder. Okay, well, you studied section 10.5. You did the MATLAB assignment number 6. You know how to parameterize a cylinder. All right, here's a picture of my cylinder here. Okay, S sub 2 now, we're just talking about the side part of the solid. Okay, so the radius is always 3 on this tin can, right? And of course, U is going to vary between 0 and 2 pi. That'll get me my circles. So, and V goes from 0 to 2. So in this situation, what I'm doing, right, is I'm stacking up a bunch of circles. Stacking up a bunch of circles to create a cylinder. And each circle has a different height. The heights go from 0 to 2. Okay, and so this is the parameterization for the cylinder. Oh, wow, okay. I'm ready to go again now to get my second surface integral. I'll compute the derivative vectors with respect to U and V. And then I'll find the cross product of those derivative vectors. And then I'll find the length of that cross product vector, which turns out to be 3. Let me give you a moment to catch up. So these problems don't have to be hard, if we're just organized. And it's very important to be organized, right? Because, it's necessary, right? Okay. Okay, so now, are we ready to move to the next page? Are there any questions? Ellie, how are you feeling about this? So far, so good? Excellent, excellent. Okay. So once again, give me a thumbs up when we're ready, when you're ready. Okay, Malik's good, Charles is good, Juliana's good, and Madeline and Gordon, wonderful. Okay. So, all right, now we compute our, let me just be a little bit, one thing here. Right, so in my work, you notice how I put the X, Y, and Z components. I try to just put this here when I do my parameterization. It just helps me follow then what I'm going to do. So the function's x squared plus y squared plus z squared. So x squared plus y squared plus z squared. And I'm going to get a new double integral, and we know how to find to compute double integrals. And turns out you'll get 124 pi. Okay, so take a moment to copy that down. Let me know if you have any questions. Okay, there's a question here. One moment. One moment. Let's see here. Hold on. Let's see. I believe it was Ellie. Why is it times 3 in the second integrand? Oh, yes, yes. Because of the 3 here. So let me see here. Let me write the formula. Let me write the yeah. Okay, good. This is this here is the length of that cross product vector. The limits are still the same. V goes from 0 to 2. U goes from, wait, hold on. Now, wait. Do I have, let me see, do I have a error here? One moment. No, that's right. That's right. That's right. It's absolutely right. Wait. Wait a minute. No, that's right. That's right. Because remember, these parameters, the cylinder, the cylinder V goes from 0 to 2 because that's the height. I was thinking V would be from 0 to 3 as for the first surface, but no, because V here means something else. V stands for like if we gosh, come on, get out there. If we stack a bunch of circles on top of each other, if the circles are at heights from 0 to 2, it'll trace out that cylinder. So absolutely, this is fine. This is fine. Okay, we got one more to go. One more to go. We got the bottom disk. So let's go now. Let's go to the bottom disk. So the bottom disk, if I just want to go back here to the picture. Okay, so the top disk had this parameterization, right? Okay, top disk had this parameterization. What would be the difference with the bottom disk, the S sub 3? And S sub 3, by the way, bottom disk is in the XY plane, right? How would I have to adjust the parameterization here to get the bottom disk? How would, what kind of adjustments would I need to make? Maybe there's no adjustment. Maybe there's, Ellie's saying the only adjustment you need to make is Z equals 0. The X and Y components are the same. And that's absolutely right. You're just tracing out a disk located in the XY plane. That's the height of 0. Good, good. So here we go. There's the bottom disk. And there's the parameterization. So I can always, if I can do the parameterizations, I can always use the same formula, you know? Okay, and so same kind of process. The cross product of u and those derivative vectors is negative vk, and essentially, we get down to here for our surface integral. So I kind of just let you copy, and I don't like to say things when it isn't necessary. I think you see what's going on. All right, let me know when you're ready to move to the next page. Let me know if you have any questions. Okay, Charles is good. Malik's good. You notice, class 2, how I label things. I label things in my work. Just helps me. Does it help you feel comfortable? Some of these, thank you everybody. Does it help you feel comfortable? Just these labels, and I don't know. I find it helpful, but how many of you find it kind of helpful to to get a feel for what we're doing? Might be nice maybe if one person said yes, even. What I'm trying to say is, you see here, like in the work. Okay, thank you, Ellie. Yeah, it's just, I try to kind of label things. All right, let's move forward. Let's get this surface integral. So the third surface integral will equal 81 pi over 2. So this means then that the entire surface in it, the surface integral over the entire surface S would be the sum of the 3 separate surface integrals added together. And when you do that, you'll get 241 pi. I'll let you copy, but are there any questions at all? Okay, Gordon, excellent. Ian's good, all right. Let me go ahead and stop the recording.